Part 2. By the end of this presentation, you should be able to calculate the molarity of 3-liter solution with 1.02 grams of dissolved sodium chloride and describe the bonding characteristics of water. So, colligative properties. Colligative properties are things like freezing point, boiling point, and they all depend on concentration. So, concentration increases with the more solute you have. So if you add more solute, your freezing point is going to be lowered. If you add more solute, your boiling point will go up. Vapor pressure, which is the ability, is just the ability to evaporate, or rate, actually it's rate of evaporation. Rate of evaporation. It goes down. It goes down if you add more solute. It doesn't evaporate as fast if you add more solute. So this is like why people that live in cold places, and the ice, the water freezes on the roads, they sprinkle salt down because it will drop the freezing point of water, meaning that water has to freeze at a much lower temperature so the roads don't freeze over. Okay, water. Water's bent shape, remember it's kind of like bent because of the lone pair, both lone pairs appear, and its ability to hydrogen bond gives it many special properties. So here, if you look here, you've got your water molecules and you have a partial positive, remember, on the hydrogen, partial negative on the oxygen, so it lines itself up to where this negative on this molecule is attracted to this positive charge on this molecule. That is a hydrogen bond, okay? Not this. That's not a hydrogen bond. This attraction right here is a hydrogen bond. So, one of its special properties is its surface tension. Because this hydrogen bond is so attractive, water has a very high surface tension. That's why these little bugs can skip across the water. It's why water droplets are round, because it's so attracted to itself, forms this nice sphere. It's also why it hurts when you do a belly flop into a pool, because you're breaking all of these attractions with your body. Alright, so why does ice float? Well, again, it's because of these hydrogen bonds. When they line each other up, it makes this crystalline structure. That's kind of hard to see. It makes this like crystalline, like honeycomb structure, and it gives you these little pockets of air in here, which decreases the density. So ice is less dense than water. That's important. Ice is less dense than water. Which is a good thing, because if ice didn't float, you wouldn't have any fish life, aquatic life, because the bottom of the lake would be frozen, and the fish and everything, all the other stuff that lives in there, couldn't survive winters. So you wouldn't have any marine life. Why is it a good thing that water has a low vapor pressure? So again, vapor pressure is like the rate of evaporation. Why is it a good thing that water doesn't evaporate very fast? Well, if it evaporated quickly, again, no marine life. Alright, the amount of solute in a solution is given by its concentration. So it's this equation right here. Molarity is moles of your solute divided by liters of your solution. So how many moles of sodium hydroxide are required to prepare 4 liters of a 3 molar solution? So I'm going to use my equation. Molarity is moles over liters, and it has to be liters. So if they give it to you in milliliters, you have to convert. So we've got, we don't know moles. We know our molarity, which is 3.0. We don't know moles, and we know we have 4 liters. So to solve for moles, 4 times 3 is 12. So I need 12 moles of sodium hydroxide to prepare that solution. What is the concentration? So here we're looking for big M, molarity, of a 5-liter solution that has 40 grams of dissolved potassium. So my equation is moles over liters. I have 40 grams of potassium, but I need moles, so I need to convert this real quick. So 40 grams of potassium, and I know for every 1 mole, my molar mass, I told you none of this goes away, is 30.9 grams. So let's see, 40 divided by 39.1, I get 1.02 moles of potassium. So that's what I'm going to use over here, 1.02, and 5 liters, so 5. So divided by 5, and my molarity is 0.204 big M. My units for molarity is big M. Dilutions. Okay, so if you have a substance, you need to dilute it because the concentration is too high, you can use this. So your initial molarity times your initial volume will equal your final molarity times your final volume. So if I have 468 milliliters of a 0.3 molar sodium fluoride solution, what will the concentration be if I add 1,060 milliliters more water to it? So I'm starting out with this, so I'm starting out with 0.3 molar times 468 milliliters. Now, as long as I keep my units the same, if this volume is milliliters, then this volume needs to be milliliters, okay? So milliliters, we're all right. If they're not, then you need to convert, make them equal, make them the same units. What will the concentration be? So I don't know my final molarity, and I'm adding 10,060 more water to it. That means I gotta take 468 and add it to 1060. So my final volume is that many milliliters. All right, so I'm just going to divide both sides by this. That cancels. Yeesh, that cancels. And so 0.3 times 468 divided by 1528 is 0.092. That's my final concentration. All right, if you can't answer the questions at the beginning of the slide, then go back and watch the practice tutorial. Whoops.